Hey everybody, welcome to another episode of EEs Talk Tech. My name is Mike Hoffman.
And I'm Daniel Bogdanoff, and this is EEs Talk Tech episode number 26, and we have Jennie Grosslight, who's also here at Keysight. So Jennie, can you introduce yourself?
Oh, good morning. Yes, I'm Keysight's memory solutions expert for protocol solutions.
Awesome.
And so what that entails is doing the planning, strategies for what products will be delivered, and then also implementing and seeing that we get products.
Awesome. So we've been kind of on a DDR kick on the podcast, so we thought we'd keep that trend going for another episode. One of the things you were talking about before we started today, you were talking about, I don't know necessarily what I can talk about in the DDR5 spec, because the spec as of today isn't public. Can you kind of, tell us all the DDR5 secrets? No.
Yeah.
Can you tell us, how does a spec go from, private to public, and who has buy-in, and kind of what does that process look like?
Right. So as a test and measurement company, we often get involved quite early, where maybe the specification is an idea with some of our key users. And then they may or may not come to us before they go to, in this case for memory, it would be going to the JEDEC to propose a specification. And a lot of times then the JEDEC will have a task force assigned to look at the new technologies. The task force will consist of any members from companies who would have a vested interest in seeing a certain new technology become a standard.
Okay. And these are usually pretty big technology companies, right, that are driving these specs, or is it small people? Or
a lot of it is driven by bigger companies because they can afford to put the money into making a new technology, right?
That makes sense.
However, there's some, smaller and mid-size. It doesn't mean that someone new with an idea can't
and so
make it happen.
So say I'm like a 5-person startup and I want a new memory technology. Do I lobby JEDEC to get that? I call Perry up, who was on the last couple episodes, and say, "Hey Perry."
Wow, yeah, that might be a little small to do it. It depends on how many backers, what kind of financing do you have? Because just the price of, I haven't checked on it, but just the price to join JEDEC might be prohibitive for too small of a company.
Okay.
But if you think about most memory technologies, you're going to have a couple players. It's going to be, there's the chipset or the memory controller.
Okay.
So who's involved in that from that angle? And then who's involved for providing the, if you're on DDR technology, you'd be talking about DRAM.
Sure.
So the actual device that stores the data.
Okay. So the, TX, RX people. Okay.
Right. And then, so typically you'd think that would be driven by the bigger players in that regard.
That makes sense.
For a new architecture. But then all the players have a voice. And you have the task force, and there's voting, and there's discussion, and a tremendous amount of work, because there's the details of the architecture have to be shown and discussed. And something that might be good for one aspect could have tremendous impact for another component.
Okay.
So it can take a bit of bantering.
Yeah.
To get it right.
Okay.
And
is all this behind closed doors, or is any of this, as far as who, the companies that are driving the new spec and the negotiations, is it all kind of behind the scenes, or is any of that made public?
Well, at first there's going to be behind the scenes even to decide whether you're going to propose it to JEDEC. And I'm sure then there's, you're going to have disclosures with your key partners to understand whether you have something that should be proposed.
Sure. Then
once you propose it at JEDEC, if you're a JEDEC member, then you can join the different task force of interest.
Okay.
So it's under the proprietary of you need to be JEDEC to see something that's just been proposed. It's not supposed to be leaked out to the broad public.
Sure.
But
Can I ask why? Like, so are if the key players are all members of JEDEC and being involved, obviously you don't want misinformation out there, but
right. Well, yeah, I'm not one of the JEDEC drivers, but if you think about it, would you really want something as you're making it and designing it? How broadly do you want to disseminate information? Like when we share roadmaps to determine making a new product or solution, we're going to go to a subset of individuals who have an interest and a need for a certain capabilities, right?
Yeah.
If you go too wide, you're spreading too much information too wide, and you get a lot of misinformation out there because some of the early discussion might not resemble the end product at all.
That makes sense. Yeah. Okay. Cool. Sorry, I know that was a little tangent from where we wanted to go. So you have worked with memory. I think you were probably even on the group that interviewed me to be in Keysight, now that I think about it. You've been doing memory as long as I've been around. What's new and exciting?
Well,
DDR?
DDR5 and LPDDR5 are coming, and they're really interesting and exciting. And then there are, the 3D, the die stacking going on. That's also very exciting. I get more involved with the DDR5 and LPDDR5 because we can probe it.
Right. Yes.
So
I've seen those probes.
I try to.
They're intense and very expensive.
Right, and it's not going to get
Super
cheaper.
high tech.
Right.
Yeah.
And physics is driving a lot about what, and always has. But then we keep pushing physics to new edges. It's like, it can't be done. We're hitting the wall. And then all of a sudden the wall moved.
Right. Fair enough. That's nice. I have a question. So, I know we did the last episode about 3D silicon, and that was a big part of our discussion. And someone in the comments on the YouTube channel asked how heat management is a thing. I don't know. I know this is not your area of expertise at all. Do you have insight into how?
I think in any device, heat management is a big deal, and whether and then you put the devices together and put them into a system and a component. Heat management is huge, and that's also part of trying to drive things at lower, so that you don't have as
run lower voltages.
Heat too, right?
That makes sense.
But it is a challenge, and I would think.
Yeah,
they get some interesting cooling heat sinks.
Like weird, like you could potentially put vias in with a heat sink that mates into that, and somehow can maybe, I don't know. I'm just making stuff up now.
We might have just invented something.
Yeah, don't publish this episode.
Go patent that immediately. Go.
You actually put the heatsink in upside down on the fins. No, sorry. So can you tell us a little bit about LPDDR5 and kind of
right? So LPDDR5 is the new low power that will be predominantly in like cell phones, and you'll also see it deployed in some of the embedded applications.
Okay.
Like LPDDR4 is actually really big in some of the automotive work now.
Interesting.
And you could see it coming out, I would expect, in some of the new autonomous vehicles.
That makes
sense.
sense.
A place where you need more memory and you need things processing to happen.
Fast. Yeah.
Fast. At least I hope that when I get in an autonomous vehicle, I hope that the processing is fast.
Yes. Super fast. Yeah. That makes sense.
So, LPDDR5 was then the next for being driven by the cell phone industry. But you think about it, the whole 5G, where we're going to have a whole different world where the bandwidths and the amount of devices that are on the network's huge. And
yeah, I think we're doing our listeners a disservice by not having a 5G episode yet. So we'll get that on the map because we need to talk about that at some point.
Yeah.
But like the latencies for 5G and the ability, this probably won't happen, but like you could do remote surgery, have someone on one half of the world doing some autonomous remote surgery on someone else, just because the latency is there and the data streams are there. And
robotically controlled
over the cell
surgical
network.
knife.
It's crazy.
Why not? Well, you certainly will be able to do like exams, I would think, if you couldn't do them now with some of the technology that exists.
Yeah, I think there's some like NGO nonprofits that do like remote stuff with cell phones, and but I don't know much about that.
And there's some tremendous improvements in that technology can offer. And the whole 5G, it's a lot of people get lost on the RF side of it, but there's the digital aspect of, well, once you've fixed the barriers and issues of getting the RF working correctly, and there's quite a few there.
Yeah.
Now you've got all these devices and have the bandwidth, and wow, opens up
I never thought about
another
that.
world here.
And like the power to process that type of information and at that speed's like
Right.
we need some battery tech improvements.
Yes, for the mobile devices, and then there's also the server database side of it. So you think about who's crunching all the information coming in from all the devices that are going to be hanging out there. And they need faster and better performance, and lower power is driving a lot of the go for DDR5. Well, you want to and LPDDR5. The idea is improve your performance, decrease your power.
Yeah,
and
twice the speeds and about half the power consumption or something like that.
Something like that.
Compared to DDR4.
And right, because you're going to double it once it achieves the final data rates.
It is
you
double
would
data
double
rate after all.
in a whole different way. Yeah, but it'll be interesting to see if those improvements are made in jumps or crawling and scraping up the ladder.
So tell us about that. What are people struggling with? I mean, I know you can't go into
physics.
Okay. So what part of physics? So
well, the whole when you start dropping the voltage swing, now you're making the eye smaller.
Okay.
And when you go faster, you make the eye smaller.
Makes sense.
You make the eye smaller, you're vulnerable to crosstalk, more vulnerable.
I think that's what Perry was saying, that in some cases DDR5 has a completely closed eye.
Yes, and that by design, they're going to have to then take care of that, dynamically equalize. So that's challenging, especially for test measurement, so that you can actually.
So it's one thing to talk, send from a
Device
transmitter to a receiver and have it work, but to make that work, you have to test it, and to test it, you have to basically, siphon that signal,
right?
Through an interposer or through. So how are people probing memory? And there's a couple different routes.
Very carefully.
Very carefully. Yeah.
Yeah, and that's just it. It's we're getting to the point where you can't touch without impacting the circuit. So definitely at the high end, there's a lot of simulation work done without a probe in the circuit, and then putting the probe in and seeing is this still going to work?
Yeah.
Right.
So are we going to be forced into a place where we just have to hope our simulations are right? And
well, who knows where we're going to go? We might go where we have some sort of device that we wave over it and can figure out what the system's going to do. I mean,
that'd be a whole nother level of noise. And
once you can sort it out.
Just call it big data and say it's going to happen, and I think we'll be on track.
Look at all the things that happened from Star Trek years ago.
Yeah,
it's like,
true.
this is Now we're all running around with quite a bit of equipment that looked like it could never happen.
Yeah, that's true. That's a good point.
Man wasn't supposed to fly.
Okay, so is it physics-wise, is it like thermal noise mostly, or is it just, shot noise inherent, like just there's always noise and...
Well, a lot of times it's the crosstalk can be a problem. And especially as you're shrinking the die even, you can get on die. And then when you're trying to transmit between, the system on chip and the memory, you have to maintain your transmission lines better. Well, so economics drives everything, right?
Sure.
And as you're making motherboards, you're trying to use the materials that have been around forever and that
Right.
are more economical. And even when that's why DDR is still around. There's the whole memory technology has been fractured a few times by, let's try another technology that should work better. And it's like, but the economics of having the whole industry change just aren't there.
That being said, I know a lot of people had predicted DDR4 was going to be the end of the line. And then I know, correct me if I'm wrong, I forget what the technology is, but no, Intel is working on their own memory technology right now that's supposed to replace DDR5 in the future. Is this, what's next? What's after? Are we even looking that far ahead yet?
Well, I think we're in a very exciting time where what's next is up for who comes up with the best idea. And that's where the reference to quite a bit of fracturing comes in, because there's a lot of really brilliant people working on the problem of how do we get more performance, how do we run faster with less power. And ideas will come up and they'll be tried, and then, well, which one actually works really well and we can reproduce it at an economical scale.
Yeah.
So
are we
there's
looking
a lot of factors?
like a materials change? You think is definitely in the cards, or what?
Well,
what are we?
There's been some material changes suggested already, and there's certainly other materials that can be better transmission lines. The problem has been, is it economically viable, right? So I think what will drive change is when the existing materials can no longer meet the performance.
Okay.
And as long as you can keep pushing, like DDR4 wasn't supposed to run as fast as they're pushing it right now.
So what's it running now publicly?
There's actually, it's being pushed to 32.
Okay.
I've got gamer PCs that we use as targets that we've pushed over to 4200 and above.
Wow. Okay.
So
Jenny's overclocking in her cubicle, and we didn't know.
overclocking and overdriving, that poor little Dave. It's like,
Yeah.
talk about heat problems.
Sure.
It doesn't help that we ripped the heat sinks off so we can put the probing
probably
on.
not.
Sometimes you have to blow fans, and
Yeah, that makes sense.
then you burn them out.
Yeah.
The gamers don't care either; they just want to play, right?
Yeah. Got to get the.
A lot of times that determines what you're doing too. It's like, what's the use model?
Sure.
Think about it. It's like, well, if you're trying to, and we talk about power being important for cell phones. Well, it's really important for a server farm too, right?
That makes sense.
You got a big data center, and if you can save power, you could be talking about millions.
Yeah, that makes sense.
Yeah. So sometimes people don't think, the cell phone or my laptop or my little pad, I want it to save power so that I don't have to charge it. And the server's plugged into the wall. Who cares? Yeah. Well, you care if you're paying the power bill, right?
Right. Yeah. Yeah. We've talked about that quite a bit in terms of building server farms in Norway because the ambient temperature is colder all year, and it's worth it to lay fiber to get a data center off in the middle of nowhere. I was thinking as we were setting up, why don't just put a data center in Antarctica or something and drop some fiber to Australia and get it on the network, and it'd be pretty cold year round.
Probably not far away from that, right?
I don't know. We'll see. It'd be interesting for sure. It's also super dry there, so I think that's good for components and stuff.
Yeah,
Better friend who's a fireman.
Up to a point, as long as there's not too much static. But then since you won't have a lot of people around
getting that. That's true. It'll be a robot server farm in Antarctica, and we just, in the winter we won't even have to access it, and all the IT people.
What a future!
Yes.
Can't wait.
Wow.
How much of this memory pushing the boundaries do you think is being driven by GDDR, and with there's all these new applications for graphics cards, coin mining, or which is the kind of the weird example, or now with VR and kind of more visually driven processes. And I think a lot of servers use graphics cards and that kind of thing as well for data crunching. Is that a big part of the kind of the push for faster DDR?
Well, GDDR's been going faster for quite a while. It's I'm not sure where it's at right now. It was at 6,400
Wow.
a long time ago. So it's a point-to-point bus, and you can do more when you're one point to one point, and instead of like with the DDR, where like you're on a DIMM and you've got multiple DRAM, and then you might put multiple, and you've got multiple ranks on the DIMM, and then you've got multiple DIMMs in the channel. There's a lot of possibility to have more reflections and more crosstalk. So that's why they've been able to go faster.
Okay. Is loading ever an issue for having multiple ranks and that type of thing where, inside of a chip, if you have multiple, can you maybe explain to people what a rank is first and then?
Yeah, so
so that I don't make a fool of myself.
in the DDR buses, and depending on the technology, how many signals of each type you have will vary. But you basically will have control signals, basically a control bus or control signals, so usually a few. And that'll be things like a chip select and maybe a clock enable, and then ODT, on-die termination control. And then you have the command, so your signals that are going to tell you, are you a read or a write, and then your address.
Okay.
Right.
Yeah.
So you've got an address and then a data bus. So you've got different signals going on there that you're looking at, and then we are gonna. If you're looking at a different rank, it's usually by chip select.
Okay.
And if you were looking at a DIMM, and if you think about how they will oftentimes have chips on either side, a lot of times it's as simple as one rank is the DIMMs on the DRAM on one side and the other rank is the DRAM on the other side.
That makes sense.
That's not always the case because designers have,
their own way of doing things.
Right. And then there'll be different standards done for how the raw card of how you can lay the chips out on a.
Well, that makes perfect sense. Yeah.
And then, but you'll have now you'd have to say, are you talking to that specific chip or that set of chips at any one time? Because they're all sharing the same data bus.
Right.
And the data, the reads and writes are all on that same data bus. But yet, you're either reading from or writing to the memory.
Right.
And so, and depending on whether you're reading or writing, the relationship of the data to the strobes that are clocking the data in will vary. So that's why if you try looking with the scope without qualifying what you're looking at on a DQ line on any of the DDR memories, it's going to be pretty ugly until you can sort out, well, when should I be looking at it so that I know when an I for a read or a write is appearing.
So you can't just go in and hook up and be like, oh yeah, this is what's happening. It has to be much
and
more
then
controlled.
of course, right, and then to save power, you're turning, they're going to normally, well, it depends on which technology you're on, but oftentimes they'll be floating it, in the center of what would be the I if they're in idle state.
Huh.
Now, some of the newer technologies, they'll be either high or low, but it depends on which one you're looking at.
Sure, that makes sense. I'm going to go back to an older question. How are you actually probing this? So I know interposers, BGA stuff.
Yeah,
what does that look like?
Well, it depends on what your use model is. So if you're looking at, say, you're building a server and you want to look at the memory traffic, usually people for servers or desktops would want to put a DIMM interposer in for logic measurements.
Can you describe to me a little bit what that looks like?
Yeah. Basically, you'd look at a DIMM socket, And the DIMM interposer will look a little bit like a DIMM module without the DRAM on it.
Okay, so a DIMM socket, this is like if you're going to add RAM to your desktop computer, it's that select.
Right. And there's different form factors. There's the regular DIMM, and then there's the small outline, which we would put in a laptop.
Sure.
Right?
Yeah.
So they're about half the size of a regular DIMM.
Okay.
And then, so the interposer is going to be about the same size as the DIMM module itself, but it's not doesn't have any of the DRAM on it. It's feeding the signals through as cleanly as possible.
So it's definitely an active
Just kind
device.
of sits,
It's
kind of
no,
sits
it's
right
passive.
between.
It's
it's
gonna,
passive.
Oh,
Okay.
preferably it's passive.
Okay.
People prefer for it to be passive, so it's basically adding trace length and a little load to every signal.
Okay.
Because you're going to feed the signal through while you probe or pick off a very little bit of energy from each of the signals so that you can look at them.
Okay.
And now, if you're with the scope, they typically will look with either a ball grid array probe underneath a particular component, or you might take the scope probe down and look at the pins, that the gold fingers on a DIMM itself. Sometimes if you're probing and wanting to look at a lot of signals, there are MSO, mixed signal oscilloscope interposers that can be inserted in, like the one that would go in for a logic analyzer.
Okay.
But the logic analyzer is looking at all the signals at once.
Yeah.
And with the scope, you're typically going to search for just a few signals at any one time.
Okay. So I know we try to avoid getting too test measurement on this podcast, but it's really cool to me. So you connect up to the logic analyzer, and this has been, historically more your expertise. And you say, oh, there might be an issue here on these couple lines. Then you go in with the scope and figure out what's happening. Or?
Right. Yeah. They complement each other nicely. Well, you think about it. If you're trying to debug or validate your design, there's different aspects. And some companies are big enough where maybe your job is the signal integrity, and you're going to be very defined on saying, I want to look at the eyes, and I want to know that I've got a big enough eye opening and under the exact conditions that you're looking at, right? And then other people might be responsible for that the protocol is correct, which means the command and address buses are telling the DRAM what it should be doing.
Okay.
And that they're doing it in the right sequence. Because if you don't do it in the right sequence, they might not get it right. And if it doesn't get it right, well, our primary objective of putting data in the DRAM and getting it out of the DRAM in the same, and having the same value, that's really the prime objective, right?
If you put in a one, you want to read a one back.
Right, yeah. And so, but if it's like, okay, so
it's like my refrigerator.
you want to validate that you did the protocol in the correct sequence. It's like, oh, did you tell it to do a read or a write too soon?
Okay.
Between each other, so.
And then you get into spec stuff where that's all laid out for you.
And that is all laid out there. And hence the reason for lots of brilliant minds to be working very hard at developing those specifications.
That makes sense.
And that's why the companies that are going to be trying to make devices that work to those specifications have a vested interest in understanding what's in the specification.
Okay.
And
makes sense.
They'll spend a lot of effort to get that right.
Okay. We're running pretty tight on time. Do you have a question? No, you didn't touch it. The data rates for DDR are always kind of marching up. What does that process look like? So you said on DDR4 we're at maybe 3200, and at some point before that we were at 2800, or I forget the intervals, but
yeah, for a while I think initially they might have been that DDR4 was expected to go to 2400, and then it's like, well, now the specification says it can go to 3200.
Okay. So the spec says, oh, yeah, you can, if you can make this work, then have
Now,
at it,
usually
or?
it's proposed by people who are pretty sure they can get there, right?
That
And
makes
it's
sense.
like, why would you propose it if you think you're going to
Right. like
fall on
open
your
the door
face,
for your
yeah.
competition to get faster than you.
Right, yeah.
DDR5 is supposed to be over 6,000. Is that right?
It's supposed to eventually get to 6,400,
It's over 9,000. Sorry. Yeah.
but the starting speed is 3,200.
Okay. That's the starting
They
speed.
typically, that is the way it goes, is that one technology, its top speed will be the beginning speed of the next
Interesting.
technology.
That makes sense.
Yeah, otherwise,
Yeah. Why bother?
why
right?
bother? Yeah. Oh, you're going to give me something new that doesn't have any improvement. It's like, well, yes, we want you to buy more.
Everyone's
That's not
keeping
a good
themselves
answer.
employed, making new specs for no reason. Yeah.
Right.
Like, stupid more. You come up with these darn laws and yeah. Okay.
Great.
Awesome. Part of our podcast, we usually don't prep our guests for this. We like to ask our guests a stupid question at the end of the podcast. So, Mike, do you have one off the top of your head?
I do.
Okay.
What's your favorite version of DDR and why?
Oh, always,
Classic Mike question.
always one that we were able to probe with the instrument of my choice.
Fair enough. That's a good answer. Okay, I know you're a dog person.
Mm-hmm.
If DDR were a dog, what breed would it be?
No, a mutt.
Okay. TBD. Awesome. So thank you, Jennie, so much for being on the podcast. Make sure you subscribe to the EEs Talk Tech podcast in your favorite podcast engine. Check us out. We have a new Keysight podcast YouTube channel. And that's all. Also, rank, review, give us 5 stars. That actually helps us be found. So we would really appreciate it.
That's how I
if you
get
do that.
paid. So please.
Yes, Mike gets paid in stars. It's like Mario and,
Are they gold?
gold plated. It depends on how many stars we get. Anyway, that's all for today. Thanks for tuning in. We'll see you next time. Next time we're going to talk about BattleBots, I think. I'm gonna go out.
Yes.
So we're going to have our first non-Keysight guest on the podcast. We're pretty pumped about this. So
Wow.
tune back in. It'll be fun. Thanks for watching and listening.